Hello everyone. Today we will study double integral. In order to understand double integral, let me first of all review single integral first. What does this single integral mean? Integral f of x from a to b. What does it mean? For this integral, you can think of this area under the curve y equal to f of x on the interval a, b. The picture looks like this. Integral from a to b, f of x dx. So that's what this integral means. This integral represents area under the curve y equal to f of x from a to b. Now, similarly, for double integral, let f of xy be a two-variable function. Let f of xy be a two-variable function. Then the graph g equal to f of xy is a surface. The graph g equal to f of xy is a surface. The double integral f of xy over r. For the double integral, we can think of the volume under the surface g equal to f of xy on the region R. Suppose that's region R, for example. Suppose that's region R. The double integral represents volume under the surface in region R, on region R. Let me draw the region R here. Suppose this is region R. The double integral f of xy over region R represents the volume under the surface over region R. That's the solid under the surface. That's the solid under the surface, g equal to f of xy. The double integral represents the volume of this solid. How do we compute? How do we find the area? How do we find the volume below the surface? Now the next question is, how do we compute the volume under the surface? Let's first of all review how we find the area below a curve first. Let's first of all review how we find area below a curve first. Let f of x be continuous. On the interval from a to b. Compute the integral f of s from a to b by finding the area under the curve y equal to f of x on the interval from a to b. We first of all sketch the graph for f of xy. Let me first of all sketch the graph first. Suppose that's the graph y equal to f of x. Suppose that's the graph y equal to f of x. A and B are somewhere on the x-axis. So we try to find the area under the curve. In order to find the area under the curve, we first of all divide interval AB into n subintervals. We first of all divide interval AB into n subintervals. Assume the partition here is xi, s1, s2, x3, and so on. The second last one is x sub n minus 1. The last one is s sub n. The width of each rectangle may be different. The width of each subinterval may be different. Someone is narrower, someone is wider. The width of each subinterval is different. Next, we pick sample point on each subinterval. Next, we pick sample point on each subinterval. So then use the sample point to approximate the height of the rectangle. So in the first subinterval, I can pick sample point to be S1 star. The sample point could be any m in the left end, right end, and could be in the middle. We pick sample point for each subintervals. In the second one, I pick x2 star. In the third one, I pick x3 star. Sample point could be anywhere in the interval. It could be in the left endpoint, right endpoint, or in the middle. And for the last one, I pick Sn star. Then we use each sample point to approximate the height of rectangles. That's f of S1 star. Then use this to approximate the height of rectangle. Then we use x2 star to approximate the height of rectangle. That's f of S2 star. Use f of S2 star to approximate the height of rectangle. F of S3 star somewhere here. Then we use f of Sn star to approximate the height for the last rectangle. Then we can try to compute the area for each rectangle. Adding up, it will be very, very close to the area under the curve. So for the approximate area, under the curve, we try to compute the area for each rectangles, then adding up. So area of the first rectangle, the height is f of S1 star. How about the width? The width we can use right endpoint minus left endpoint. That's called delta S1. Use right endpoint minus left endpoint. That's the width of the first rectangle. For the second rectangle, the height is f of S2 star times the width of the rectangle. The width we can use right endpoint minus left endpoint. x2 minus s1. Let's call this delta x2. So delta s1, delta s2, and the last one is delta sn. Use the height f of Sn star times delta Sn. Then I can write this in sigma notation. I from 1 to n. Here, the index varies. S1 delta S1, S2 delta S2. The index varies. We can use I to represent the index. Si star delta Si. That's the approximate area That's the approximate area under the curve. And this is called Riemann Sum. This is called Riemann Sum. If we try to find the actual area under the curve, we need to take very small intervals. So for actual interval under the curve, for actual area under the curve, we must make each interval very small. So we take a limit as the largest. Delta Si approach to 0. If the largest delta Si goes to 0, every subinterval will be very small. If the largest one goes to 0, every subinterval will be very small. If I take this limit, it will be the actual area under the curve. And that's the definition of the integral from a to b, f of x dx. That's the definition of integral. However, how do we use this limit to find the area under the curve? It's very hard to take this limit here. Is there a better version? Let's reconsider this problem over. In the beginning, we divide the interval AB into n subintervals, where each interval has different widths. Or if we divide AB into n interval, where each interval has exactly the same width. If we make delta S1 equal to delta S2 equal to delta Sn, if we make every subinterval have the same width, then we can let delta x represent delta Si, since they are all the same. I from 1 to up to n. Since they are all the same, I can let delta x represent delta Si. Then delta s is the width of each interval. How do we compute delta x? We can take the total width divided by the number of subintervals. Total width from a to b is b minus a. And the number of subintervals is n. So that's delta x, the width of each subinterval. Next, for the sample point. Sample point could be any point in the interval. Sample point could be any point in the subinterval. It could be left endpoint, right endpoint, or point in the middle. Let's make it easier. Let's use right endpoint to be the sample point. If I use right endpoint to be the sample point, then if we choose right endpoint to be the sample point, then in the first subinterval, f of S1 star will be f of S1. So S1 star will be S1. In the first interval, I choose right endpoint to be the sample point. So S1 star will be the same as S1. In the second interval, in the second subinterval, X2 star will be S2. In the third one, X3 star will be X3. And in the last one, Xn star will be Sn. Sn star will be Sn. So if we make this change, then S as n goes to infinity, delta x will approach to 0. As n goes to infinity, delta x will approach to 0. So the maximum of SI, maximum of delta SI will be 0. Therefore, this limit is equivalent to the limit n approach to 0, sigma notation I from 1 to n this limit is equivalent to the limit n approach to 0, sigma I from 1 to n. F of Si star is the same as f of Si. Delta Si is the same as delta x, where delta x equal to b minus a over n. How about Si? Is there an easier way to write Si? Observe here. I can write S1. As a plus delta x. I can write x2 as a plus twice delta x. I can write x3 as a plus 1, 2, 3, a plus 3 times delta x. So in general, if we see the pattern, we can write Si as a plus I delta x. So Si can be written as a plus I delta x. That's the simpler version. Finding area under the curve. That's the simpler version. Next, I'll show you how to find volume under a surface. It's very, very similar. Volume under the surface is very, very similar as area under the curve. Let's look at this example. Let R equal to AB cross CD be a rectangular region in the xy plane. Assume f of sy is continuous on R. Compute the double integral f of sy over region R by finding the volume under the surface g equal to f of sy over R. Let me first of all draw a rough graph for the surface g equal to f of sy. That's x-axis, y-axis, z-axis. Assume the surface g of sy looks like this. Assume that's the surface g of sy. R is a region in the xy plane. Let me draw R in the xy plane. Let me draw region R in the xy plane. Let R be a rectangular region in the xy plane. Assume that's R in the xy plane. Assume that's region R in the xy plane. X is from A to B. So that's A, that's B in the x-axis. And Y is from C to D. That's C and D in the y-axis. Now, Double integral represents the volume under the surface g of f of g equal to f of sy. Let me draw the surface. Let me draw the volume under the surface here. That's the volume under the surface. That's what we are looking for. That's the volume under the surface, g equal to f of sy over region R. That's what we are looking for. Let me draw this region over. Let me pull it outside. Let me draw it like this. That's the volume under the surface, g equal to f of sy. And this is region R. Next, let me draw region R in the sy plane. That's x-axis. That's the s-axis. That's the y-axis. Assume this is region R in the SY plane. Assume this is region R in the SY plane. I draw this region R in the SY plane. So A is here, B is here, C is here, and D is here. AB, that's the interval AB in the x-axis. That's the interval CD in the y-axis. We try to compute the volume under the surface over this region R. First of all, I divide the interval AB into n subintervals. Then A will be x sub 0. X sub 1 is here. That's x sub 2. That's x sub 2. That's x sub I minus 1. That's x sub I. The second last one is x sub n minus 1. And b is x sub n. Then, since I divide interval AB into n subintervals, I divide region R into n strips. Based on these subintervals, I divide region R into n strips. That's the first strip, second strip. That's an I strip. That's an ice strip. That's an I subinterval in the x-axis. And that's the last one. That's an I strip. That's the first strip, second strip, and that's an ice one. That's an I subinterval in the x-axis. That's an I subinterval in the x-axis. This strip in the picture looks like this. Assume that's x sub I minus 1. This is x sub I. This strip looks like this. This strip in the 3D graph looks like this. And the volume under the surface over this strip looks like this. Next, let me draw the volume under the surface over this strip. Next, let me draw the volume under the surface over this strip. That's the volume under the surface over this strip. Let me pull it outside. Let me pull it outside and draw it here. That's the volume under the surface g equal to f of sy over this strip, the ith subinterval in the s-axis. The ith subinterval in the s-axis. Next, I divide the interval ct into m subintervals. I divide interval ct into m subintervals in the y-axis. So c will be y sub 0. That's y sub 1, y sub 2. Let's call this y sub j minus 1. That's y sub j. The second last one is y sub m minus 1. D is y sub m. The second last one is y sub m minus 1. D is y sub m. Then I will cut region R into m by m subrectangles. Then I cut region R into m by m subrectangles. This is the jth subinterval in the y-axis. This is the jth subinterval in the y-axis. The intersection between the I subinterval in the s-axis and the j subinterval in the y-axis is this rectangular box. That's the intersection between the I subinterval and in the x-axis and the j subinterval in the y-axis. The intersection of these two subintervals is a rectangular box. Next, let me draw this rectangular box in the picture, in the 3D picture. So this is x sub I minus 1, x sub I is here. Assume this is y sub j minus 1. This is y sub j. Then that's the rectangular box. This is this rectangular box. This represents this rectangular box in the 3D graph. Next, let me try to draw the volume under the surface over this rectangular box. Next, let me draw the volume under the surface over this rectangular box. It looks like this. That's the solid under the surface over this rectangular box. Let me draw this outside. Let me draw this solid here. That's the solid over this rectangular box, this small rectangular box under the surface. Next, we try to find a volume for this solid. Next, we try to find a volume for this solid. This solid, it looks like a rectangular box. It looks like a rectangular box. So we try to use the rectangular box to approximate the volume of this solid. And we know that the volume of a rectangular box is always the base area times the height. For this solid, the base area is the area of this rectangular region, which is the same as the area of this rectangular region here. Since this rectangular region is the intersection between the I subinterval in the x-axis and the j subinterval in the y-axis, we can use delta A sub ij to represent the area of this rectangular box. So the area of the base area is delta A sub ij. Next, how about the height? What should we use for the height of this rectangular box? We know that in this surface, the height is different in different places. So in order to approximate the height, we pick a sample point of this rectangular region. Pick a sample point of this rectangular region. Pick any point here. Call this point is the sample point. We use xi star, comma y sub j star represent the sample point. So we use this point xi star, comma y sub j star as a sample point of this region. Then we use the sample point to approximate the height of this rectangular box. So assume that's f of xi star and y sub j star in the surface. If I pick si star, y sub j star as a sample point, the point on the surface will be f of xi star, y sub j star. So that's the point on the surface. Then we try to use this point to approximate the height of the rectangular box. It looks like this. The rectangular box looks like this. That's a rectangular box approximated by this point, f of si star, y sub j star. So we can see that the volume of this rectangular box is very, very close to the volume under the surface over this rectangular region. So the height of this rectangular box is f of xi star, comma y sub j star. So the volume under the surface over this rectangular region can be written as f of si star, comma y sub j star times delta A sub ij. That's an approximate volume under the surface over this rectangular box. If I find the sum as j goes from 1 to m, then I add up the total volume under the surface over every rectangular boxes here in this column. So this expression represents the total volume under the surface over this strip. This expression represents the total volume under the surface over this strip, which is the volume of this solid. If I find a sum as I goes to n, then I add up the total volume under the surface over every strip here. Then I add up the sum of total volume under the surface over every strip here, which represents the total volume under the surface over this region. So this expression represents the total volume under the surface over this region R, which is the volume of this solid, the same as the volume of this solid. So that's an approximate volume under the surface over region R. This is an approximate volume under the surface over region R. This is an approximate volume under the surface g equal to f of sy over the rectangular region R. So this is an approximated volume under the surface g equal to f of sy over region R. So the approximated volume under the surface is the summation I from 1 to n, summation j from 1 to m, f of si star comma y sub j star times delta a sub ij. This formula has a name, it's called a double Riemann sum. This formula has a name, it's called a double Riemann sum. This is the double Riemann sum, which represents approximated volume under the surface over region R. Now, how do we find the actual volume under the surface over region R? For the actual volume under the surface, we need to take a limit. Take a limit as the maximum delta Si goes to 0 and the maximum delta y sub j goes to 0. Summation I from 1 to n, j from 1 to m, f of si star, comma y sub j star times delta a sub ij. When I take a limit as maximum delta si goes to 0 and maximum delta sj goes to 0. In the picture, it looks like this. In the x-axis, the width of the first interval is delta si, delta s1. The width of the second interval is delta x2. And the width of the ith interval is delta si. The width of the last interval is delta sn. In the y-axis, the width of the first interval is delta y sub 1. The width of the second interval is delta y sub 2. The width of the j subinterval is delta y sub j. And the width of the last subinterval is delta y sub m. If I take a limit as the maximum delta si goes to 0, that means in the x-axis, the largest subinterval, the width of the largest subinterval goes to 0. That means every subinterval will be very, very close to 0. The width of every subinterval will be very, very close to 0. And same thing, when the maximum delta y sub j goes to 0, that means in the y-axis, the width of every subinterval will be very, very close to 0. And when the width of every subinterval in the x-axis and width of every subinterval in the y-axis goes to 0, the area of every rectangular box will be very, very small. The area of every rectangular box will be very, very small. So the volume under the surface will be very, very close to the actual volume under the surface. So the volume under the surface will be very, very close to the actual volume under the surface. That's the actual volume under the surface when we take a limit. And this is the definition of the double integral. This is the definition of the double integral. Double integral over region R, f of sy dA. That's the definition of the double integral. However, if we try to use this limit to compute a double integral, it's very, very hard. It's very hard to compute this limit here. So, is there a better way to compute a double integral? Let's reconsider this problem over. In the beginning of the problem, we divide the interval AB in the x-axis into n subintervals, where each interval may have different widths. Now, if I divide interval AB into n subintervals, where each interval have exactly the same width, if we use subintervals with exactly the same widths, if we use the subintervals with exactly the same width, then delta S1 will be the same as delta S2. The width of the first subinterval will be the same as the width of the second subinterval, and will be the same as the width of the third interval. So the width of every subinterval will be the same. If they are all the same, I can call this equal to delta x. So let delta x represent the width of every subinterval in the x-axis. Then delta s can be computed using the formula b minus a over n. B minus a represents the total width of this interval AB. Then divided by n subintervals. That's the width of each subinterval. And similarly, in the beginning of the problem, we divide the interval CD in the y-axis into m subintervals. Divide interval CD in the y-axis into m subintervals, where each interval may have different widths. Now, same thing, if I divide interval CD into m subintervals with exactly the same widths, then delta y1 will be the same as delta y2. The width of the first interval will be the same as the width of the second interval. It will be the same as the width of the third interval. So the width of every subinterval will be the same. If they are all the same, I can use delta y represent the width of each subinterval in the y-axis. Then delta y can be computed using d minus c over m. D minus c represent the total width of the interval in the y-axis. Then take the total width divided by m subintervals. That's the width of each subinterval. Next, since we use the intervals with the same length, same width in the x-axis and the y-axis, then for every rectangular region here, their length must be the same. Also, their width must also be the same. Since for every rectangular region they have the same length and the same width, then the area of each rectangular region must be the same. Then the area of each rectangular region must be the same. So the area of each rectangular region must be the same. If we use the subintervals with the same width, then the area of each rectangles must be the same. So delta A sub ij, if it's the same, then we can say delta sub A of ij equal to delta A with for all I from 1 to n and j from 1 to m. That means the area of every rectangle must be the same here. If they are all the same, I let delta A sub ij equal to delta A. Delta A sub ij equal to delta A for all I from 1 to n and for all j from 1 to m. And also, delta A can be computed by using delta x times delta y. Delta A can be computed by using delta x times delta y. So this is delta A, that's delta x, that's delta y. Delta x times delta y is delta A. So the area of each rectangle can be computed by using delta x times delta y. Next, let's reconsider the sample points. In the beginning of the problem, on each rectangular region, we choose the sample point to be a random point on the region. Now, we choose the sample point to be the right upper corner. Now on each rectangular region, we choose the sample point to be the right upper corner. Then the sample point here will be xi, comma yj. If we choose a sample point to be in the right upper corner on each rectangular region, then the sample point here will be xi, comma yj. So on each rectangular region, let the sample point be in the right upper corner. Then the sample point in the right upper corner. Then the sample point si star, comma y sub j star will be xi, comma y sub j for all I and j. For all I from 1 to n, and for all j from 1 to m. Then we can rewrite these limits here. A simpler way to write the limit is I from 1 to n, j from 1 to m, that stays the same. Since we choose a sample point to be in the right upper corner, xi star yj star will be xi, comma yj. And since the area of each rectangular region is the same, delta sij will be simply written as delta a. Now, how about the limit? How to do the limit? For the limit, let's consider a different limit. If I take a limit as n goes to infinity, then delta x as n goes to infinity, delta x is b minus a over n. That's a constant, that's infinity. Constant over infinity is 0. Then delta x approaches to 0. So the largest subinterval delta si will also approach to 0. And similarly, as m goes to infinity, then delta y will be 0. D minus c is a constant. If m goes to infinity, constant over infinity is 0. So as m goes to infinity, delta y goes to 0. So the maximum delta y sub j goes to 0. So this limit is equivalent to the limit as this limit as n goes to infinity and m goes to infinity. This limit is equivalent to this limit. Maximum delta si goes to 0 and maximum delta y sub j goes to 0. This limit is equivalent to this limit. So this is the simpler version of the double integral f of sy over region R. In this limit, delta a equal to delta x times delta y. And delta x can be computed as b minus a over n. Delta y can be computed as d minus c over m. How about si, yj? How about s sub I, y sub j? Look at the picture. S1 can be written as a plus delta x. S1 can be written as a plus delta x. S2 can be written as a plus delta x twice. S2 can be written as a plus delta x twice. And x3 can be written as a plus delta x 3 times. So in general, xi can be written as a plus delta x I times. So delta I xi equal to a plus I delta x. Si can be written as a plus delta x I times. So Si equal to a plus delta x, a plus I delta x. Similarly, in the y-axis, y1 equal to c plus delta y. y1 equal to c plus delta y. y2 equal to c plus delta y twice. y2 equal to c plus delta y twice. y3 equal to c plus delta y 3 times. So in general, y sub j equal to c plus j times delta y, 3j times delta y. In general, yj equal to c plus delta y, j times. So yj equal to c plus j delta y. That's the formula for xi and yj. So xi can be computed using a plus I delta x, and y sub j can be computed using c plus j delta y. This is a simpler version of the double integral. This is the definition of double integral, but it's too hard to compute this limit. So that's a simpler version of the definition of the double integral. This is a simpler version of the definition of double integral. Using this limit, the computation will be much easier. So that's the definition of double integral. And this is a simpler version of the definition of double integral. Memorize the formulas. Next, let's do some example about double integrals. First example, consider the function f of sy equal to s squared plus 2y over the rectangular region R equal to 0, 6 cross 0, 4. Part A. Divide R into A equal subregions with n equal to 2, m equal to 4, and choose the left upper corner as the sample point on each subregions. Estimate the value of the double integral. So if we divide region R into A equal subregions, that means the subintervals on the x-axis and the subintervals on the y-axis must be the same. So if they are the same, let's compute delta x, delta y first. If all subintervals has the same width, delta x is b minus a over n. A and b is the interval on the x-axis. A and b is the interval on the x-axis. Here is 0, 6. So plugging 0 for A, plugging 6 for B. N equal to 2. 6 divided by 2 is 3. Delta y is d minus c over m, where CD is the interval on the y-axis, which is 0, 4. So we plug in 0 for C, plug in 4 for D. M is 4. I get 1. Next, based on delta x, delta y, we can find delta A. Delta A equal to delta x times delta y, which is 3. That's the region of each. That's the area of each subregion. Next, since we use left upper corner as sample point, let's draw the subregion first. Then we can choose the left upper corner as sample point. Let's draw the subregions first. X is from 0 to 6. Y is from 0 to 4. That's region R. Here, since n is 2, we divide x-axis into two pieces. We divide the interval on the x-axis into two subintervals. Delta x is 3, so 0 plus 3 is 3, 3 plus 3 is 6. And here m is 4, so we divide the interval 0, 4 into 4 subintervals. Delta y is 1, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So here we have 8 subregions. 1, 2, 3, 4, 5, 6, 7, 8. On each region, let's choose the sample point. The sample point is the left upper corner. So for the first rectangle, this is the left upper corner. For the second rectangle, this is the left upper corner. For the third rectangle, this is the left upper corner. For the fourth one, this is the upper corner, left upper corner. For the fifth one, this is left upper corner, next one. This is left upper corner. Next, this is left upper corner, next one. This is the left upper corner. Next, we try to find the volume of the rectangles on each subregions. We try to find the volume of the rectangular box over each subregions. On the first region, the height is f of, on the first region, sample point is 0, 1, so the height is 0, 1 times delta A. On the second region, on the second subregion, the height is 3, 1. This point, 3, 1. The area is delta A. Next one, the height is f of 0, 2. F of 0, 2. Let me put it here. Times delta A. The height times base area is the volume of the rectangular box. Next one, sample point is 3, 2. F of 3, 2 times delta A. Next one, f of 0, 3 times delta A. Next one, f of 3, 3 times delta A. Next one is f of 0, 4 times delta A. Next one is f of 3, 4 times delta A. If I add them up, we can see that here delta A is a common factor. I can pull it outside. Then we have f of 0, 1 plus f of 3, 1 plus f of 0, 2, f of 3, 2 plus f of 0, 3, f of 3, 3, f of 0, 4 plus f of 3, 4. We know that delta A is 3. F of 0, 1. We substitute 0, 1 into the original function. Substitute 0, 1. 0 squared plus 2 times 1 is 2. Substitute 3, 1. 3 squared plus 2 is 11. Substitute 0, 2. Substitute 0, 2. 0 plus 4 is 4. Next, substitute 3, 2. 3 squared is 9. 2 times 2 is 4. 9 plus 4 is 13. Next, substitute 0, 3. 0 plus 6 is 6. Next, substitute 3, 3. 3 squared is 9. 3 times 2 times 3 is 6. 9 plus 6 is 15. Next, substitute 0, 4. 0 squared plus 2 times 4 is 8. Next, substitute 3, 4. 3 squared is 9. 2 times 4 is 8. 9 plus 8 is 17. Then adding up. I use calculator, get 76. Then 3 times 76 is 228. That's the estimated value of the double integral. With the same problem, part B, divide region R into 6 equal subregions with n equal to 3 and m equal to 2, and choose the midpoint as the sample point on each subregions. Estimate the value of the double integral f of sy over region R. So since we are using equal subregions, that means the subinterval on the x-axis must have the same width, and the subintervals on the y-axis must also have the same width. So I can find delta x using the formula b minus a over n. Here, a and b are the interval on the x-axis. A and b represent interval on the x-axis, which is 0, 6. So 0 is a, 6 is b. Divided by n, a is 3. 6 divided by 3 is 2. Then for delta y, we use the formula d minus c over m. C and d represent interval on the y-axis, which is 0, 4. So 0 represents c, 4 represents d. We have 4 minus 0 over m. M is 2, which is also 2. So delta A is delta x times delta y, which is 4. Next, let's try to draw the region. Because we use midpoint as a sample point on each subregion, let's draw the region first. Then we can find the midpoints. Let's draw the region first. Zero, 6 by 0, 4. Then, since n is 3, we divide the interval on the x-axis into 3 regions, into 3 subintervals. Delta x is 2. 0 plus 2 is 2. 2 plus 2 is 4. M is 2. We divide the interval on the y-axis into 2 subintervals. Delta y is 2. 0 plus 2 is 2. Two plus 2 is 4. Next, we try to find a midpoint on each subregion. On the first subregion, the midpoint on the x-axis is 1. Midpoint on the y-axis is 1. So this point is 1, 1. Second region, midpoint on the x-axis is 3. Midpoint on the y-axis is 1. This point is 3, 1. Next region, the midpoint on the x-axis is 5. Midpoint on the y-axis is 1. This point is 5, 1. Next, midpoint here is 1, 3. Midpoint here is 3, 3. And midpoint here is 5, 3. So the double integral is approximately the volume of the rectangular boxes on each subregion. So the volume of the rectangular box on the first subregion is the height, base area times height. The height is, on the first subregion, the height is f of 1, 1 times the area. Height times base area is the volume of the rectangular box. On the second region, volume of the rectangular box on the second region is f of 3, 1 times delta A. The height times the base area. Volume on the third region is f of 5, 1 times delta A. On the fourth one, volume on the fourth region is f of 1, 3 times delta A. On the fifth one, f of 3, 3 times delta A. Volume on the sixth subregion is f of 5, 3 times delta A. Then we try to add them up. First of all, delta A is the same. I can pull it outside. If I pull out delta A, I have f of 1, 1 plus f of 3, 1 plus f of 5, 1. Plus f of 1, 3 plus f of 3, 3 plus f of 5, 3. Then we know that delta A is 4. For f of 1, 1, for this value, we plug in the value into the original function. If I plug in 1, 1, 1 squared plus 2 is 3. If I plug in 3, 1, 3 squared plus 2 is 11. If I plug in 5, 5 squared plus 2 is 27. If I plug in 1, 3, 1 squared plus 6 is 7. If I plug in 3, 3, 3 squared plus 6 is 15. If I plug in 5, 3, 5 squared plus 6 is 31. Then I used my calculator. 3 plus 11 plus 27 plus 7 plus 15 plus 31 is 94. And 4 times 94 is 376. That's the estimated value of the double integral. Part C. Find the actual value of the double integral. If we try to find the actual value of double integral, we need to use the definition. We can use the simpler version. This is the simpler version of the definition. So, first of all, we need to compute delta x, delta y. Delta x is b minus a over n. Which is 6 minus 0 over n, which is 6 over n. Delta y is d minus c over m, which is 4 minus 0. Over m, which is 4 over m. Then based on delta x, delta y, we compute delta a. Delta A is 24 over n times m. We multiply delta x and delta y. Next, compute SI. SI is a plus I delta x. Here a is 0. I delta x. Delta x is 6 over n. So if I multiply out, I get 6i over n. Let's compute y sub j. Y sub j is c plus j times delta y. C is also 0. J times delta y. Delta y is 4 over m, which is 4j over m. Next, we plug in si yj into function f. So the double integral f of double integral over region R. F of sy dA is the limit as n goes to infinity, limit as m goes to infinity, summation I from 1 to n, and take summation j from 1 to m. F of si comma yj means I plug in si into the function, plug in yj into the function. If I plug in si yj, I have 6i over n square plus 2 times 4j over m times delta A. Delta A is 24 over n times m. Let's simplify. Next, let's simplify this limit. I have limit n goes to infinity, m goes to infinity, sigma I from 1 to n, j from 1 to m. 6i squared over n can be rewritten as 36i squared over n squared. 2 times 4j over m can be rewritten as aj over m times 24 over mn. To make it a little easier, I pull out 24, write 24 all the way to the front, make it a little easier. Pull out 24, write 24 all the way to the front, it'll be a little easier. Next, I distribute 1 over mn into the parentheses. Distribute 1 over mn into the parentheses. I have 36i squared over mn cubed plus aj over m squared n. Next, we take care of the inner summation. We take care of inner sum. Take care of the inner sum first. So we leave the outer sum the same. N approach to infinity, m approach to infinity. Outer sum stays the same. For the inner sum, I can split it into 2 summations. J from 1 to m, 36i squared over mn cubed plus the summation j from 1 to m aj over m squared n. Now let's simplify the summation. Keep limit the same. For the first sum here, The index is j. Index is j. So we treat I, m, n as constants. So I can bring all constants to the front. I have 36i squared over m n cube. Summation j from 1 to m of 1. If I bring everything to the front, I write 1 here. Next, since index is j, I treat m and n as constants. I can pull it outside. I pull out a over m squared n. Summation j from 1 to m of j. Then evaluate each summation here. Evaluate each summation. I have 24 times the limit n approach to infinity, m approach to infinity, keeping the outer sum the same. Summation of 1 from 1 to m is m. Summation of 1 from 1 to m is m. Then summation of j from 1 to m is m times m plus 1 over 2. That's one of the special formulas for summation. Have to memorize it. There are 4 formulas. You need to memorize it. Summation I from 1 to n of 1 is n. Summation I from 1 to n of I is n times m plus 1 over 2. Summation I from 1 to n of I squared is n times m plus 1 times 2n plus 1 over 6. Summation of I from 1 to n of I cube, that's n squared times m plus 1 squared over 4. You need to memorize these 4 special formulas here. For summation of j from 1 to m, it matches this formula here. Here, I represent j, n represent m, so I have m times m plus 1 over 2. Then simplify this part. We have 24, limit n approach to infinity, limit m approach to infinity, I from 1 to n. For the first term, I can cancel m. If I cancel m, I have 36i squared over n cube. Second term, a divided by 2 is 4. I can cancel 1 of the m. I have 4 times m plus 1 over mn. Like a divided by 2 is 4. I cancel 1 of the m. I have mn on the bottom. Next, take care of the outer sum. Limit n goes to infinity. Limit m goes to infinity. I first of all split this into 2 summations. I from 1 to n of 36i squared over n cube plus summation I from 1 to n of 4m plus 1 over mn. Since I'm taking summation with index I treat n is a constant. Everything other than I is a constant. Here I treat mn as a constant. So it can be rewritten as 24 limit n goes to infinity, m goes to infinity. I can pull out 36 over n cube. summation I from 1 to n of I squared. Next one, we only consider I as a variable. Everything other than I is a constant, since the index is I. Everything other than I is a constant, so here I pull out everything. I have 4 times n plus 1 over mn times summation I from 1 to n of 1. If I pull out everything, I have to write 1 here. We cannot leave it blank. Next, let's simplify. 24, limit n approaches to infinity, m approaches to infinity, 36 over n cubed. The sum of I squared, I from 1 to n, is n times m plus 1 over 2n plus 1 over 6. Second one, 4 times m plus 1 over mn. The sum of 1, where I goes from 1 to n, that's n. Next, let's simplify. That's 24 times the limit n goes to infinity, m goes to infinity. 36 divided by 6 is 6. I can cancel 1 over the n from top and bottom. I have 6 times n plus 1 times 2n plus 1 over n squared. Cancel 1 over the n. I have 4 times m plus 1 over m. This limit can be rewritten as limit n goes to infinity, m goes to infinity. It can be rewritten as 6 times m plus 1 over n times 2n over n plus 4 times m plus 1 over m. This can be rewritten as 1 plus 1 over n, 2 plus 1 over n. That's 1 plus 1 over m. As m and n go to infinity, that 1 over n becomes 0, 1 over n becomes 0, 1 over m becomes 0. So I get 24 times 6 times 1 plus 0, 2 plus 0, plus 4 times 1 plus 0, which is 24 times 12 plus 4 is 16. 24 times 16. I get 384 in the calculator. So that's the actual value of the double integral. Wow, this way doesn't look too simple. Is there an easier way? Next, let me introduce Fubini Theorem. According to Fubini Theorem, there is an easier way to compute double integrals. Fubini Theorem says, if f is continuous on the rectangular region, r equal to the closed interval ab cross the closed interval cd, then the double integral f of sy over region R is the outer integral dx x from a to b, inner integral y from c to d f of sy, or it can be rewritten as outer integral y from c to d, inner integral x from a to b f of sy. What does these two integrals mean? That's our first time seeing this integral. What does these two integrals mean? Here, let me introduce the notation. The first integral, we treat dx as an outer integral, dy as the inner integral. We evaluate the inner integral with respect to y first. With respect to y means we treat s as constant. We only treat y as a variable. Everything other than y, we treat it as a constant. So we evaluate the inner integral with respect to y first. Then we will have a function of x. Since I treat x as a constant, we will have a function of x here. Then we evaluate an outer function with respect to x. And for the other one, dy is the outer integral. So here we evaluate the inner integral first. If I evaluate the inner integral, I treat x as variable, y as constant. So I take integral with respect to x. Solve the integral, I will have a function of y. Then evaluate the outer integral with respect to y. According to Fubini Theorem, as long as f is continuous and region R is a rectangular region, it doesn't matter if I evaluate y first or I evaluate x first. The answer for both integrals must be the same. Now, let's redo the previous problem using Fubini Theorem and solve it in two ways. So, double integral f of sy over region R. It can be written as integral x from 0 to 6, y from 0 to 4. F of sy is s squared plus 2y dy dx. That's first way. We evaluate dy first. When I evaluate dy, I leave the outer integral the same. For the inner integral, take entire derivative with respect to y. I treat s as constant. So s squared is a constant. Its entire derivative is x squared times y. Integral of a constant is constant multiplied by the variable. Take entire derivative for 2y. I have y squared. Then evaluate y from 0 to 4. X from 0 to 6. If I substitute 4 for y, I have 4x squared plus 16. If I substitute 0 for y, I get 0. Solve the inner integral, I have a function of y. Then I can use it to evaluate the outer integral. Take entire derivative with respect to y. I have integral x from 0 to 6. If I take entire derivative, I have 4x cubed over 3 plus 16x. Evaluate from 0 to 6. If I plug in 6 cubed is 216. 216 times 4 divided by 3. If I use calculator, I get 288. Plug in 6 here. 16 times 6 is 96. 288 plus 96 is 384. Next, a second way. If I solve it in a different order, I take integral y from 0 to 4 first. X from 0 to 6. F of sy is x squared plus 2y. Dx, dy. The variable must match. The variable must match. If we put dx here, it doesn't match, it won't work. If I put dy here, it won't match. The variable must match. Next, we solve the inner integral first. When we solve the inner integral, we treat x as a variable, y as a constant. So I have s cubed over 3 plus 2xy. I treat 2y as a constant. So antiderivative of a constant is the constant multiplied by the variable. Evaluate at s equal to 0 and s equal to 6. Leave the outer integral the same. Y from 0 to 4. I substitute 6 for x. 6 cubed is 216. 216 divided by 3 is 72. I substitute 2 for x. 2 times 6 is 12. I get 12y. When I substitute 0, I get 0. Then I take outer integral. This is a function of y. I can take outer integral. When I take outer integral, 72 antiderivative is 72y. And for 12y, antiderivative is 6y squared. I evaluate for y from 0 to 4. If I substitute 4, 72 times 4 is 288. If I substitute 4 here, 4 squared is 16. 16 times 6 is 96. 288 plus 96 is 384. So in both ways, we get exactly the same answer. Next, let's do some computation for double integrals. Integral from 1 to 2. The other one is from 0 to 4. 2sy dy dx. So here we solve the inner integral first. Take antiderivative with respect to y. If I take antiderivative with respect to y, I treat x as constant. So I have 2xy squared over 2. 2 and 2 will cancel. We have sy squared. Evaluate from 0 to 4 dx. If I substitute 4 for y, I have 16x. If I substitute 0 for y, I get 0. Then this is a single variable function with respect to x. This is a single variable function. I take antiderivative with respect to x. I have ax squared. Evaluate from 1 to 2. If I plug in 2, I get 32. Plug in 1, I get a. Together is 24. Next example. Integral from 0 to 3. Another integral from 0 to 2. 4 minus y squared dy dx. So here we must solve the inner integral first. We take antiderivative with respect to y. Leave the outer integral the same. Take antiderivative with respect to y. Here I treat 4 is a constant here. Take antiderivative, I get 4y. Take antiderivative for y squared, I get y to the power 3 over 3. Evaluate from 0 to 2. Keep the outer integral the same. If I plug in 2, I have a minus a over 3. If I plug in 0, I get 0. Simplify. A minus a over 3 is 16 over 3. Take antiderivative, we have 16 over 3x. 16 over 3 times x. Evaluate from 0 to 3. If I substitute 3, I get 16. If I substitute 0, I get 0. So the answer is 16. Next example. Integral from 0 to 3. Another integral from -2 to 0. X squared y minus 2sy dy dx. So here we must solve the inner integral first. Take antiderivative with respect to y. We leave the outer integral the same. Take antiderivative with respect to y. We have x squared times y squared over 2 minus xy squared. Take antiderivative with respect to 2. I treat x as constant. Evaluate y from -2 to 0. Leave dx the same. Evaluate y from -2 to 0. Leave x the same. If I substitute 0, I get 0. If I substitute 0 for y, I get 0. If I substitute -2 for y, Negative 2 squared is 4. 4 over 2 is 2. I get 2x squared for the first term. If I substitute negative 2 for y here, negative 2 squared is 4. 4 times x is 4x. Then simplify, we have 0 minus 2x squared minus 4x, which is 4x minus 2x squared dx. Evaluate the integral with respect to x. We have 2x squared minus 2x cubed over 3. Evaluate the integral from 0 to 3. If I substitute 3, 3 squared is 9. 2 times 9 is 18. If I substitute 3, 3 cubed is 27. 27 divided by 3. 27 divided by 3 is 9. 2 times 9 is 18. 18 minus 18 is 0. Next, this is example 3. Next, example 4. Evaluate the integral from 1 to 4. The other one is from 0 to 4. X over 2 plus square root of y dx dy. Here, we must evaluate the inner integral first. Take antiderivative with respect to x, which means I treat y as a constant. So leave the outer integral the same. Take antiderivative with respect to x. I have x squared over 2 is over 4. I treat y as a constant, so square root of y is a constant. Antiderivative of a constant is the constant multiplied by the variable. Then evaluate x from 0 to 4. Evaluate x from 0 to 4. If I substitute 4 for x, 4 squared is 16. 16 over 4 is 4. If I substitute 4 for x, I have 4 radical y. If I substitute 0 for x, I get 0. This is a single variable function of y. Next, I take antiderivative with respect to y. Antiderivative of 4 is 4y. Antiderivative of 4 square root of y, that's 4y raised to 3 over 2 divided by 3 over 2. Evaluate from 1 to 4. Let me simplify the integral first. 4y stays the same. 4y raised to 3 over 2 divided by 3 over 2 means we multiply by the reciprocal. So we have 4 times 2 over 3, which is a third. Y raised to 3 over 2. Evaluate from 1 to 4. If I plug in 4, 4 times 4 is 16. If I substitute 4 here, 4 raised to 3 half is a. A over 3 times a is 64 over 3. If I substitute 1, 4 times 1 is 4. A over 3 times 1 is a over 3. Then I have 92 over 3. Using my calculator, I get 92 over 3. Next, let me introduce a property about double integral. Suppose function f1 of x is continuous on the interval ab, and the function f2 of y is continuous on the interval from c to d. Then the double integral x from a to b, y from c to d, f1 of x times f2 of y, dy dx can be written as a product of two single integrals, where x from a to b, f1 of x dx, and y is from c to d, f2 of y dy. This property says, if the integrand of a double integral can be written as a product of function of x times function of y, if the integrand of a double integral can be written as a product of function of x times function of y, and all the limits here are constants, then we can split this double integral into the product of two single integrals. We can compute each integral individually, then multiply the answer together. Let me give you a proof about this property. It's very simple. So let's start from double integral. X is from A to B. Y is from C to D. We have f1 of x times f2 of y dy dx. This is a double integral. The integrand is a product of two functions, function of x times function of y. And all the limits are constant. Here, when we are solving the inner integral, we take an antiderivative with respect to y. So we consider function of x is a constant. When we are taking antiderivative with respect to y, we consider function of x is a constant. Since function of x is a constant, I'm allowed to bring the constant outside the integral. I'm allowed to bring the constant outside the integral. So this integral can be rewritten as f1 of x times the integral y equal to y from c to d, f2 of y dy dx. This is the inner integral. Next, this is a single variable integral. This is a single integral here. This is a single integral. f2 of y is continuous. Y is from c to d. This is a single integral. If we evaluate a definite single integral, this is a constant. If we evaluate a definite single integral, this is a constant. Then we have a constant times a function inside the integral. If we consider an outer integral, we have a constant times the function inside the integral. Then we can bring this constant outside the outer integral. Then we can bring this constant outside this outer integral. So bring the constant outside the outer integral. We have y from c to d, f2 of y dy. This is definite integral, which is a constant. I can bring it outside. Then what's left is, if I bring this outside, what's left in the integral is x from a to b, f1 of x times dx. If I bring the constant outside, that's what's left in the integral. Then this integral can be rewritten as x from a to b, f1 of x dx times y from c to d, f2 of y dy. That's the proof. So for double integral, if the integrants can be written as a product of function of x times function of y, and the limits are constants, we can split the double integral into two single integrals, then compute each integral individually, then multiply the answer together. That's the same answer as the double integral. Next example. Integral from -1 to 2. Integral from 0 to pi over 2. Y times sine of x dx dy. Let's observe this function first. Here the integrand is a product of function x times function of y, and all the limits are constant. Then by the previous property, I can write it as a product of two single integrals, where x from 0 to pi over 2 sine x dx times integral of y from -1 to 2 y dy. By the previous property, if the integrand is a product of function x times function of y, and all the boundaries are constant, then by the previous property, I can write this as a product of two single integrals, where x is from 0 to pi over 2, y is from -1 to 2. Then we take each single integral individually. If I take the first single integral of sine x is negative cosine. Evaluate from 0 to pi over 2. If I substitute pi over 2, cosine pi over 2 is 0. If I substitute 0, cosine 0 is 1. Then solve the second integral. antiderivative of y is y squared over 2. Evaluate from -1 to 2. If I substitute 2 squared is 4, 4 over 2 is 2. If I substitute -1 squared is 1, 1 over 2 is a half. Then multiply together. 1 times 2 minus half is 3 half. Next example. Integral from 0 to 1, from 1 to 2, x, y, ex, dy, dx. So this I can write it as a product of function x times function of y. I can write it as y times x ex. Since I can write the integral as a product of function x times function of y, and all the limits are constants, I can separate this double integral into 2 single integrals. Integral of x is from 0 to 1, x times ex dx. Integral of y is from 1 to 2, y times dy. Then we solve each integral individually. If we solve the first integral, we need to use integration by parts. If we solve the first integral, we need to use integration by parts. Integral from 0 to 1, x ex dx. Use integration by parts. Let u be x. Let dv be e to the power of x. Then take integral for u. du is dx. Take antiderivative for dv. v is e to the power of x. Then use the formula u times v minus integral of v times du. Leave the first one the same. Evaluate this integral first. Integral of e to the power x is e to the power x. Then we can evaluate both of them together. X e to the power x minus e to the power x from 0 to 1. If I substitute 1, I get e. If I substitute 1, I get another e. If I substitute 0, I get 0 minus e to the power 0 is 1. E minus e is 0. Minus -1 is +1. So this integral is +1. And if I solve this integral, that's y squared over 2 from 1 to 2. If I plug in 2, I get 2. If I plug in 1, I get half. 2 minus half is 3 half. Next. Evaluate the double integral square root of x over y squared dA, where r is the region or point of sy in R2 such that x is between 0 and 4, y is between 1 and 2. How do we solve this integral? Here we can see that this R is the rectangular region. X is from 0 to 4, y is from 1 to 2. This R is a rectangular region. So by Fubini Theorem, this double integral can be rewritten as square root of x over y squared dA. This double integral can be rewritten as integral x from 0 to 4, y from 1 to 2. It's Fubini Theorem. Square root of x over y squared dy dx. That's Fubini Theorem. Then by the previous property, I can write this part. I can write the integrand as a function of x times function of y, and all the limits are constants. Then I can separate this into two single integrals. Let me rewrite the integrand first. The integrand x over y squared. The integrand x over y squared can be rewritten as square root of x over y squared. It can be rewritten as square root of x times y raised to -2. So since I can write the integrand as a product of function x times function of y, I can separate this double integral into two single integrals. So here x is from 0 to 4, square root of x dx. Y is from 1 to 2, y raised to -2 dy. Then we can solve each integral individually. Solve the first integral, I get x raised to 3 over 2 times 2/3. Evaluate from 0 to 4. Second integral, we have y raised to -1 over -1. Evaluate from 1 to 2. And the second integral can be rewritten as -1 over y from 1 to 2. Now let me evaluate the first integral first. If I substitute 4 raised to 3/2 is 8. So I get 3 over 2 times 8. If I plug in 0, I get 0. Second integral. If I substitute 2, I get -1/2. If I substitute 1, I get -1. So minus -1 is +1. First parenthesis, if I multiply out, I get 16 over 3. For the second parenthesis, if I add them up, I get half. 16 over 3 times half is 8 over 3. Next example, evaluate the double integral of x squared minus y squared over x squared plus y squared squared over region R, where R is the set of Sy in R2, such that S is between 0 and 1, and Y is between 0 and 1. So for this double integral over region R is a rectangular region with x between 0 and 1, y between 0 and 1. So if we apply Fubini Theorem, this double integral x squared plus x squared minus y squared over x squared plus y squared squared dA. This double integral can be rewritten as the outer integral x from 0 to 1, inner integral y from 0 to 1, x squared minus y squared over x squared plus y squared squared dy dx. Then we evaluate the inner integral first. What should we do for the inner integral? We are taking antiderivative with respect to y. So here, for the inner integral, we can apply Trig Substitution. Here we have y squared, on the bottom we have y squared plus s squared. We can apply Trig Substitution. So let y equal to x tangent theta. When we have u squared plus a squared, we let u equal to a times tangent theta. Here, y is the variable, s is constant. The denominator is more complicated. We need to take care of the denominator first. So y is a variable, x is a constant. So I let y equal to x times tangent theta. Apply Trig Substitution here. Then, if I substitute and replace each y with x tangent theta, the inner integral can be rewritten as x squared minus, if I plug in, I have s squared tangent squared theta. And the denominator can be rewritten as s squared plus s squared tangent squared theta squared. dy can be rewritten as x secant squared theta d theta. So dy can be rewritten as x secant squared theta d theta. dx stays the same. Here, let me keep the variable as y. I'll change the variable back to y later and keep y here. Then I try to simplify the integrand. On the numerator, I can factor power x squared. If I power x squared, I have 1 minus tangent squared theta. On the denominator, I can also power s squared. If I power s squared, I have s squared squared, which is x raised to power 4. If I power s squared, I have s squared squared, which is x raised to power 4, times 1 plus tangent squared theta squared times x times secant squared theta d theta. dx stays the same. Next, I can cancel s squared from top and the bottom, and cancel 1 of x from the top and the bottom. After cancellation, there's 1x left on the bottom. I leave the top the same. 1 minus tangent squared theta, leave the top the same. On the denominator, 1 plus tangent squared theta is secant squared theta. 1 plus tangent squared theta is secant squared theta squared. Since I cancel this x, I have secant squared theta d theta left. Then I can cancel secant squared from top and the bottom. Cancel secant squared here. What's left is 1 minus tangent squared theta over x times secant squared theta. I cancel secant squared from here, from top and the bottom. d theta dx. Since we are doing d theta, we treat x as a constant. I can pull x outside. I can pull out this x. I pull out this x. Since this x is on the denominator, it should be 1 over x. Then what's left is 1 over secant squared theta minus tangent squared theta over secant squared theta d theta dx. Then one over secant squared theta is cosine squared theta. Tangent squared theta over secant squared theta, what do we get? Tangent squared theta over secant squared theta. Tangent squared theta can be rewritten as sine squared theta over cosine squared theta. Secant squared theta can be rewritten as 1 over cosine squared theta. Then keep the top the same. Flip the bottom over. I get cosine squared theta over 1. Then I can cancel cosine squared theta. What's left is sine squared theta. So tangent squared theta over secant squared theta is sine squared theta. d theta dx. What's cosine squared theta minus sine squared theta? There's a formula. Double angle formula says cosine 2 theta is cosine squared theta minus sine squared theta. This is called a double angle formula. Cosine 2 theta is cosine squared theta minus sine squared theta. So cosine squared theta minus sine squared theta is cosine 2 theta. If I take antiderivative with respect to x, with respect to theta, I have 1 over 2 sine 2 theta. Evaluate y from 0 to 1. But here the variable is x. So the variable is theta. I must change theta to x. The variable is theta. I must change theta to x. We have 1 over x times 1 over 2 sine 2 theta. Sine 2 theta can be rewritten as, use double angle formula, sine 2 theta can be rewritten as 2 sine theta times cosine theta. That's another double angle formula. Sine 2 theta is 2 sine theta cosine theta. So sine 2 theta can be written as 2 sine theta cosine theta d theta. No more d theta, sorry. Y is from 0 to 1 dx. So here, I leave 1 over x the same, 1 over 2 the same. I will write sine 2 theta as 2 sine theta cosine theta. 2 sine theta cosine theta. Evaluate y from 0 to 1. Then, let me rewrite this integral. 1 over x times 1 over 2 and times another 2. These two get cancelled. I get 1 over x times sine x cosine x. What's sine x cosine x? I try to write sine x cosine x in terms of y. So I need to draw a triangle here. We have y equal to x times tangent theta. That means tangent theta equal to y over x. Tangent theta equal to y over x. If I draw a triangle, tangent is opposite over adjacent. Tangent is opposite over adjacent. If I use Pythagorean Theorem, I have square root of x squared plus y squared. Use Pythagorean Theorem for the missing side. So refer to this triangle. Sine theta is opposite over hypotenuse. Opposite over hypotenuse is y over square root of x squared plus y squared. Cosine theta is adjacent over hypotenuse. Adjacent over hypotenuse. X over square root of x squared plus y squared. Then here I can cancel x from top and the bottom. On the top we have y left. Y times 1 is y. On the bottom, square root of x squared plus y squared times square root of x squared plus y squared, I have x squared plus y squared. Evaluate y from 0 to 1. If I plug in 1, for y, I have 1 over x squared plus 1. If I plug in 1 for y, I have 1 over x squared plus 1. If I plug in 0 for y, I get 0. So I have integral from 0 to 1. 1 over x squared plus 1 dx. Then apply. Then take antiderivative with respect to x. Take antiderivative with respect to x. And we know that the formula for the integral for 1 over u squared plus 1 du is inverse tension of u plus c. That's the formula for inverse tension. Integral of 1 over u squared plus 1 du is inverse tension of u plus c. So if I apply the formula here, I have inverse tension of x evaluate from 0 to 1. If I plug in 1, I get inverse tension of 1 minus inverse tension of 0. Inverse tension of 1 is pi over 4. Inverse tension of 0 is 0. So the answer is pi over 4. The answer looks weird. Can we check the answer? Can we check the answer? One way to check the answer is we can solve integral in the opposite order. We can do dx first, then do dy. If the answer is correct, we should get exactly the same answer. Next, in order to verify the answer, we try to take integral in the opposite order. We previously take integral in the order of dy dx. Now we try to take integral in the order of dx dy in the opposite order. So the procedure is the same. We try to solve the inner integral first. So leave the outer integral the same. For the inner integral, we try to take antiderivative with respect to x. Take antiderivative with respect to x. So again, we need to use trig substitution. The bottom looks more complicated. So let's take care of the bottom first. So for trig substitution, when we have u squared plus a squared, we let u equal to a times tension theta. So here, since x is a variable, y is a constant, I let x equal to y tension theta. Since x is a variable, y is a constant, I let x equal to y tension theta. Let me keep the limit as x. I'll change it back later. I'll change the variable back to x later. So if I substitute x, I have y squared times tension squared theta minus y squared over y squared tension squared theta plus y squared square, and dx can be written as y secant squared theta d theta. Dx is y secant squared theta y secant squared theta d theta. Leave dy in the same. Y is from 0 to 1. Then on the numerator, I can factor y squared out. I get tension squared minus 1. On the denominator, I can factor power y squared. If I power y squared, I have y squared square, which is y raised to power 4. On the denominator, what's in the parentheses is tension squared plus 1 squared, y times secant squared theta d theta times dy. Then I can cancel y squared from top and the bottom and cancel 1 over the y here. Then what's left is a y on the bottom. On the bottom, tension squared theta plus 1 is secant squared theta. Leave the top the same. If I cancel y, the top stays as tension squared theta minus 1. And we have secant squared square on the bottom. This y can cancel. We have a secant square here. Secant squared theta d theta times dy. Then I can cancel secant square. If I cancel secant square, there's a secant square left on the bottom. Leave the top the same, d theta dy. Since we're taking antiderivative with respect to theta, which is y as a constant, I can pull y outside. Pull this y outside the integral, I get 1 over y. Then what's inside here? I can take tangent square theta divided by secant square theta minus 1 over secant square theta times d theta dy. Then tangent square theta over secant square theta, tangent square theta over secant square theta is sine square theta. One over secant square theta is cosine square theta, d theta dy. Now we have sine square theta minus cosine square theta. Since cosine square theta minus sine square theta is cosine 2 theta, then if we switch order, sine square theta minus cosine square theta will be negative cosine 2 theta. If we switch order, it will be negative cosine 2 theta. It will be negative cosine 2 theta, d theta dy. Next, if we take antiderivative with respect to theta, if we take antiderivative with respect to theta, we have negative 1 over 2 sine 2 theta. X is from 0 to 1. So in order to evaluate the integral, we must write theta in terms of x, write function theta in terms of x. Here, apply double angle formula for sine 2 theta. Sine 2 theta is 2 sine theta cosine theta. Then these two get cancelled. I get 1 over y, negative 1 over y. These two get cancelled. I get negative 1 over y times sine theta times cosine theta. S is from 0 to 1 dy. But since we try to evaluate x, we need to write function of theta in terms of x. So we try to draw a triangle here. X equal to y tangent theta. If I solve for tangent theta can be rewritten as x over y. If I draw a triangle, theta is here, tangent is opposite over adjacent. Tangent is opposite over adjacent, so that's opposite, that's adjacent. And if I use Pythagorean Theorem, the missing side here is s squared plus y squared, square root of s squared plus y squared. So tangent theta is opposite over hypotenuse. Sorry, sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. So this integral can be rewritten as negative 1 over y. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. X is from 0 to 1 dy. So I rewrite sine theta as x over square root of s squared plus y squared. I rewrite cosine theta as y over square root of s squared plus y squared. Then evaluate x from 0 to 1. Let me simplify first before I evaluate. I can cancel this y from top and the bottom. What's left is negative x over s squared plus y squared. S is from 0 to 1 dy. If I plug in 1 for x, I have negative 1 over s squared plus y squared. If I plug in 0 for x, I get 0. If I plug in 1 for x, on the bottom it should be 1 plus x, 1 plus y squared. So the integrand here is negative 1 over 1 plus y squared dy. I can pull out negative sign. 1 over 1 plus y squared dy. If I use the formula, antiderivative of 1 over u squared plus 1 du is inverse tension of u plus c. Antiderivative of 1 over u squared plus 1 du is inverse tension of u plus c. So the antiderivative of 1 over 1 plus y squared, it should be inverse tension of y. Evaluate from 0 to 1. If I plug in 1, I get inverse tension of 1. If I plug in 0, I get inverse tension of 0. Minus negative inverse tension of 0. Inverse tension of 1 is pi over 4, because tension to the tension of 45-degree angle is 1. And double negative become positive. Inverse tension of 0 is 0. And so it's negative pi over 4. We get a completely different answer. For the first part, when I take integral in the order of dy dx, the answer is positive pi over 4. When I take integral in the order of dx dy, I get negative pi over 4. That's a completely different answer. Let's look at the problem over. Did we make any mistake? The problem is this integral, s squared minus y squared over s squared plus y squared squared over region R. R is the technical region with x between 0 and 1, y between 0 and 1. And here we apply Fubini Theorem. Here we took integral for x from 0 to 1, y from 0 to 1, dy dx. For the other integral, we took integral for y from 0 to 1, x from 0 to 1, dx dy. Everything looks correct, but what's the mistake? Everything looks correct. What's the mistake? Be very, very careful. Here we did make very, very serious mistake. Remember, for Fubini Theorem, it says, if the integrand is a continuous function over a rectangular region R, then we can apply Fubini Theorem. Is this integrand continuous on region R here? Is this integrand a continuous function on region R? On region R, x varies from 0 to 1, including 0 and 1. Y varies from 0 to 1, including 0 and 1. If I plug in 0 to this function here, I get 0 over 0, which is undefined. That means the integrand is not a continuous function over this region R. The integrand is not a continuous function over this region R. So we are not allowed to apply Fubini Theorem. Since the integrand is not a continuous function over region R, we are not allowed to apply Fubini Theorem for this integral. But if we can use Fubini Theorem, then what can we do for this integral? For this integral, its integrand is undefined at point 0, 0. That means it has a discontinuous integrand. This integral has a discontinuous integrand. We must consider this as an improper integral. So for improper integral, we use a limit. For improper integral, let me rewrite the integral, this integral here. This integral can be rewritten as limit as u approach to 0 from right side, v approach to 0 from right side. Double integral over region R, s squared minus y squared over s squared plus y squared squared dA, where R is a rectangular region from u to 1 cross the interval from v to 1. If we take a limit, u approach to 0 from the right side and v approach to 0 from the right side, then this function will be continuous over this rectangular region R. If I use a limit here, u is very, very close to 0, but it's not 0. V is also very, very close to 0, but it's not 0. Then this integral is continuous over this rectangular region R. Then we can use Fubini Theorem for this integral. Then we can apply Fubini Theorem for this integral. Here, this limit can be rewritten as limit u v approach to 0, 0. X is from u to 1. Y is from v to 1. X squared minus y squared over x squared plus y squared squared dy dx. If I treat this as an improper integral, I can set out like this. I take a limit as uv approach to 0 from the right side. Then r is this rectangular region R can be rewritten as x from u to 1, y from v to 1. This is a rectangular region, and 0 is not included. 0 is not included in region R. Then this integral is continuous on this region R. I can apply Fubini Theorem. Next, I solve this integral. So keep a limit the way it is. We must always keep a limit. uv approach to 0, 0. X is from u to 1. Now I take antiderivative with respect to y. Next, I take antiderivative with respect to y. If I take antiderivative for this function with respect to y, the work is the same. Doing a long process, the work is the same. Eventually, the antiderivative is y over x squared plus y squared. This is the antiderivative of this with respect to y. This is the antiderivative of this function with respect to y. The work is the same. The work is exactly the same. This is the antiderivative of this function with respect to y. So the antiderivative of this function is y over x squared plus y squared. Evaluate y from v to 1 dx. Evaluate y from v to 1. If I plug in 1 for y, I get 1 over x squared plus 1. If I plug in v for y, I get v over x squared plus v squared dx. Next, take antiderivative with respect to x. Keep the limit the way it is. For the first part, if I take antiderivative with respect to x, I get inverse tension of x. For antiderivative of 1 over x squared plus 1, apply this formula here. I get inverse tension of x. Then how about antiderivative of this function? For the integral of v over x squared plus v squared dx, I can first of all pull out v, then I get 1 over x squared plus v squared dx. Next, the formula says integral of 1 over u squared plus a squared. This formula is 1 over a times inverse tension of u plus c. So if we apply this formula, over x represent u, v is a constant that represents a. So I have 1 over v. Applying the formula, I get 1 over v times inverse tension. So the formula here should be u over a. So if we apply the formula, it should be the variable over the constant, x over u. U over a is the variable over the constant. So it should be x over v, the variable over the constant, plus c. And v get cancelled. We get inverse tension of x over v plus c. This is the antiderivative of v over x plus v squared. So for v over x plus x squared plus v squared, its antiderivative is inverse tension of x over v. And this is definitely integral. We don't need to add constant c. Evaluate x from u to 1. Evaluate x from u to 1. Then if I plug in 1, for x, I get inverse tension of 1 minus inverse tension of 1 over v. If I plug in u for x, I get inverse tension of u minus inverse tension of u over v. Then it can be rewritten as inverse tension of 1 is pi over 4 minus inverse tension of 1 over v minus inverse tension of u, double negative is positive, plus inverse tension of u over v. Next, we take a limit as u and v approach to 0, 0. If this limit exists, then we say this improper integral converges. If this limit does not exist, then we say this improper integral diverges. Let's take limit. When we take limit as uv approach to 0, 0, this is a two-variable function. So I can consider 0, 0 as a point in the uv plane. We can consider 0, 0 as a point in the uv plane. Consider this is the u-axis. This is the v-axis. Consider 0, 0 as a point in the uv plane. We can try to take limit along different paths. We can try to take limit along different paths passing through this point. If the limit along two different paths is different, then the limit does not exist. But if the limit along every path passing through this point is the same, then the limit exists. Let's do some path tests first. Let's first of all test this line. This line is the v-axis. In the v-axis, this line can be expressed as u equal to 0. In v-axis, this line can be expressed as u equal to 0. So along the path, u equal to 0, which is the v-axis, along the path u equal to 0, which is the v-axis, this limit can be rewritten as 0, comma v approach to 0 from right side. Pi over 4 minus inverse tension of 1 over v minus inverse tension of 0 plus inverse tension of 0 over v. Then this limit can be rewritten as limit v approach to 0 from right side. V approach to 0 from right side. Pi over 4 minus inverse tension of 1 over v. Inverse tension of 0 is 0. And this is also 0. Inverse tension of 0 is 0. So this limit can be written as limit v approach to 0 from right side. Pi over 4 minus inverse tension of 1 over v. If I plug in 0 from right side, 1 over 0 from right side is positive infinity. 1 over 0 from right side, this is positive infinity. 1 over 0 from right side, this is positive infinity. Inverse tension of infinity is what? The graph of inverse tension looks like this. Upper bound is pi over 2. Lower bound is negative pi over 2. The graph of inverse tension looks like this. This is a graph of y equal to inverse tension of x. So inverse tension of infinity approach to pi over 2. Inverse tension of positive infinity approach to pi over 2. So we have pi over 4 minus pi over 2. Inverse tension of infinity is pi over 2. Pi over 4 minus pi over 2 is negative pi over 4. So the limit along the path, along the y-axis, along the v-axis is negative pi over 4. Next, let's take limit along a different path. Let's consider limit along the u-axis. Let's consider limit along the u-axis. The u-axis can be written as v equal to 0. The u-axis can be expressed as v equal to 0. Next, let's take limit along the path. V equal to 0, which is in the u-axis. Which is the u-axis in the uv plane. Take a limit. We have u comma 0 approach to 0, 0 from right side. Pi over 4 minus inverse tension of 1 over 0. Since v approach to 0 from right side, here it should be 1 over 0 from right side minus inverse tension of u plus inverse tension of u over 0. Since v approach to 0 from right side, it must be 0 from right side. Then simplify. This limit can be rewritten as limit u approach to 0 from right side pi over 4 minus inverse tension of 1 over 0 from right side. 1 over 0 from right side, 1 is positive, 0 from right side is also positive. Positive number over positive number is positive. 1 over 0 is infinity. So you get inverse tension of infinity. Inverse tension of infinity is pi over 2 minus inverse tension of u plus inverse tension of u over 0 from right side. Before we take a limit, this u is a constant. A constant over 0, a constant over a very, very small number is a very, very large number, is infinity. And u is also positive. Positive number over positive number is positive. A fixed number over 0 is infinity. So we get positive infinity. Inverse tension of infinity is pi over 2. Then here, positive pi over 2 and negative pi over 2 can cancel. We get limit as u approach to 0 from right side. Pi over 4 minus inverse tension of u. If I plug in 0 here, inverse tension of 0 is 0. So the answer is pi over 4. Here we can see that the limit along two different paths is different. The limit along two different paths is different. If the limit along two different paths is different, the limit does not exist. Since the limit along two different paths is different, this limit does not exist. So the limit does not exist. If the limit does not exist, that means the double integral diverges. This improper double integral diverges. So this improper double integral diverges. Finally, as a conclusion, when we are taking double integral over a rectangular region R, in general, we apply Fubini Theorem. However, be very careful. If the integrand is not a continuous function over the rectangular region R, we are not allowed to apply Fubini Theorem directly. Be very careful.